Welcome back, everybody. This video is talking about electricity and magnetism, and at the end, you're going to see how these two terms are connected. This is actually part one of a two-part video, and in fact, it might even extend a little bit beyond. This is kind of a complicated connection that we're going to see, and so we're going over the broad ideas in this video, and then we're going to see some nuances, because there are definitely some small intricacies that make this a little bit tougher. So first, the big ideas. Part A has us remembering electric fields. Now, we've seen electric fields, especially if you're in my own class, and if you've seen some of my prior videos. Electric fields are a direct result of this electric force equation, also called Coulomb's law. Remember, we learned how positive and negative charges can attract. All right, positive and positive or negative and negative charges, they will repel each other, okay? Now, that is ultimately due to this thing known as Coulomb's law, but these forces, because this attraction and or repulsion can act at a distance, we learned that scientists represent this with fields. We went to, if you're in my own class, a website that looks like this. Thank you to Phet for making a whole bunch of simulations that I'm going to use. Links in the description in this video below if you want to mess around. One Phet simulation was us using charges to try to get this little charge here into a goal. If you remember, the way we represent fields, and in this visual, it's showing the electric field by these little black and white arrows. A positive little charge would have a field that looks like this, because if you remember, we would pretend to reach into our pocket and plop down a little positive. This positive would repel from this positive. That's why you have these arrows, all right? That's what the direction means. Now, in this diagram, I can actually change it so that this little hockey puck is actually negative. What do we know about negative and positives? Negative and positives will attract. They like each other. Notice that's actually a little weird now because the field lines were drawn when we were pretending to drop in positives. So these arrows, they're not changing because we're always pretending when we draw or when we represent these arrows, we're always pretending to drop in little positives. But if I make my charge a negative, my hockey puck a negative, well, negative is opposite of a positive. So you're going to see that this negative charge is actually going to move in the opposite direction as these arrows. It's not that these arrows are wrong. It's not that there's not an electric field anymore. There's definitely still this electric field from this positive charge, but the negative charge is going to move in the opposite direction. We can still kind of use it as a map, just knowing that if the arrows are pointing, say, to the left, the negative charge is going to feel a force to the right and vice versa, okay? But anyway, we've seen electric fields before. Now, back to my slides. Part B, there is another force that we actually may not have talked about before in this class or in this sequence of videos, and that's magnetism. I bet in one way or another you're somewhat familiar with magnets. Maybe you have a refrigerator magnet. Maybe you've messed around and you've seen that magnets can attract things like paper clips. Maybe you've gotten a couple of magnets and you've noticed that not only can magnets attract each other, but sometimes magnets can repel. In fact, maybe you've messed around with a compass. A compass is, in fact, actually a small little magnet that's balanced well so that the magnet can rotate and spin. You could even grab a refrigerator magnet or a big bar magnet or horseshoe magnet like this. If you bring it close to a compass, again, which is another magnet, well, it'll react. But even without getting into the equation for magnets, you are likely familiar with this idea that magnets can act at a distance. So with that in mind, how can magnets push or pull objects like paper clips or even like this compass? How can they push or pull things at a distance? What's the word? It's a word that starts with an F. It is, again, fields. We won't worry about an equation, but because magnets can also act at a distance, it's worth being familiar with this idea of magnetic fields. And for that, I have another simulation. This right here is a bar magnet. We're not going to worry too much about the fine details of magnets, certainly not here, but magnets have a north pole and a south pole, kind of similar to how charges had a positive and a negative. And what you're seeing in this other Phet simulation is in the background, they are representing the magnetic field. If I could plop down a little magnet, like a little south pole, that actually has some nuances that we won't get into. That little south pole would want to attract to this north pole. And here I have a compass, okay? Remember, a compass is itself a little magnet. So if I move this magnet around, the compass is going to react. And in fact, this compass here is going to align itself. It's going to match this magnetic field. Okay, so something potentially new. There are magnets. Magnets do exert a force, and we can represent that force at a distance with magnetic fields. Okay, back to my set of note slides. The magnetic force fields can get complicated. We've seen that sometimes with multiple electric charges and that electric force field. Similarly, for a horseshoe magnet, the magnetic field looks kind of like this. The Earth itself, based on some internal mechanisms in the Earth generates its own magnetic field. You may be familiar with that idea already. All right, that's in fact why we kind of make compasses in the first place, because we can use a compass and it can align with Earth's magnetic field so that, especially in the early days before a lot of modern technology, we could figure out the direction, north, south, east, and west. Okay, so we reminded ourselves about electric fields. We have learned, or maybe just recognized, that magnets exist. Magnets exert a force, and we've seen that magnets have a force field because that force acts at a distance. Now is kind of the crux of this video. 4 facts about electricity and magnetism. If you're in my own class, we may have already have seen this in action. If not, that's okay. I'm kind of going to show you some examples along the way. This is our first fact, okay? Electric fields move electrons. Now, we've seen this before. In fact, I showed you in this simulator right here that if I have a negative electron, well, negative electrons are attracted to positive charges. We can see the electric field. This electron is reacting. It is moving due to the electric field. It is weird because it's kind of opposite based on how scientists decided to draw electric fields, but regardless, it's still true that what do we know? Electric fields will move electrons. If I have an electric field if I have an electron in the presence of an electric field, that electron is going to move. Next fact. All right, this was fact number 1. This is fact number 2. Magnetic fields will cause magnets to move. Magnetic fields move magnets. We could see that if you actually had a compass and a magnet, bring the magnet close to the compass, at a distance, that compass is going to move. It's going to swing around. We saw it in the simulator just a couple moments ago. If I drag this bar magnet around, this bar magnet has its own magnetic field. The compass in that online Phet simulator would react. Magnetic fields will move magnets. A compass is a magnet, so having this bar magnet nearby will cause this compass to move. It'll cause it to align in a specific way. That is fact number 2. We have 4 in total. The third fact, moving electrons, which, by the way, that's the same thing as saying electric current. That's the same thing as saying electricity. If I have electricity, or if I have moving electrons, that will in fact create a magnetic field. Everybody, this is new. We have not seen this before in my video. If you're in my own class, you may have seen this in action with a miniature lab that we've done. I can show this idea that if I have moving electrons, I can create a magnetic field. I'm going to go to another Phet simulator right here. This website is showing that I have a battery and I have just a loop of wire. Now, if I have this battery and I turn it off, what I've done is I kind of changed the battery, so instead of spitting out some voltage, it's spitting out 0 voltage. It's like I no longer have a battery in there, all right? Now, if there's no battery, or if the battery is completely dead, there's no electricity, there's no moving electrons. Well, there's nothing going on with this compass, with this magnet right here. But if I actually have electrons moving, notice, all of a sudden, I have a magnetic field. So creating or causing electrons to move in a loop of wire will create a magnetic field, and it's moving, or it's going with this wire. It wasn't just in the background, it's because of this loop of wire. I'm trying to show that by moving this around. Again, if I turn the battery off, nothing. But if I have electricity flowing, all of a sudden I have a magnetic field. What's the cause of this idea? To be honest, we're not going to get into it really in this class, but just treat this as a fact. If I have moving electrons, that creates a magnetic field. Okay, my 4th and final bullet point after seeing this guy in action, all right? Moving magnets will create electric fields. Okay, we have not seen that before in this video. If you're in my own class, we may have done a mini lab where we were dropping objects in this coil of wire and we were detecting some electricity, but this is a fact. Moving magnets create electric fields. I can show that with one final Phet simulation. This one actually looks very, very similar to the prior one, but in this one, I'm not really going to move this coil around. I'm going to move this magnet. Remember, magnets have a magnetic field because of that magnetic force. When I have this bar magnet just at rest, notice, the electrons aren't moving. Like nothing's happening. The light bulb is at rest. But if I take this magnet, and if I can move it, if I'm moving it around, what do you notice about those electrons in the wire? As I'm moving this magnet around and around, the electrons start wiggling. Moving electrons, that's electricity. So by moving this magnet, I am actually causing these electrons to move. I wish this website showed an electric field being generated, because admittedly, that's what this is saying more directly, but indirectly, we're seeing this fact. If I have this bar magnet and I move it around and around, or if I kind of drop it through, I'm causing electrons to move. If I get a magnet to move around, well, I do the same effect of having an electric field. field. Okay, so those are our 4 physics facts. They are located right here, all right? Team, this is kind of the core idea now of this physics video, seeing these 4 facts and noticing something, okay? I'm going to tell you a bit of a story. The story is going to start down here. It says, moving magnets create electric fields. That's how we're going to start, okay? I have a moving magnet, or if I had a moving magnet, moving that magnet will create an electric field. Okay, great, you might think. But notice something. If I have an electric field, well, this bullet point from before says, if I have an electric field, that will move electrons. So if I move a magnet, that's going to create an electric field. And by creating an electric field, that will allow me to move an electron. So by effect, moving a magnet will allow me to move an electron. Okay, but if we keep going with this story, if an electric field moves an electron, moving electrons, electricity, that's going to create a magnetic field. It's another step. It's another path in my journey. Moving a magnet will create an electric field. That is going to cause electrons to move, and moving electrons are going to create a magnetic field. So moving a magnet does this, this does this. This is going to cause a magnetic field to be generated. And what happens when I create a magnetic field? Well, a magnetic field will then move a magnet. Okay, so notice each of these steps so far have connected with another step. A moving magnet makes an electric field, that moves electrons, that creates a magnetic field. Magnetic fields are then going to move magnets. And what's going to happen when I move a magnet? I'm back where I started. A moving magnet creates an electric field. Everybody, this is a story. Moving magnets create an electric field, which are going to move electrons. Those moving electrons are going to create a magnetic field. That magnetic field is going to move magnets, and that moving magnet is going to create an electric field. And then everybody, I could keep going. This is actually kind of a never-ending story. One of these statements creates the next statement, which creates the next statement, which eventually gets me back to where I started, and this process continues. Electricity and magnetism, everybody, they are not really two separate things. In school or just in life, you've likely thought about electricity as a separate entity, a separate topic, and maybe if you've talked about this in science classes before, maybe you've talked then adjacent about magnets. But it turns out electricity and magnets are not really their own thing. They are part of the same physics phenomena, the same idea. Scientists call this electromagnetism. It's not really valid to think of them as separate things. They're really one in the same. One idea almost creates the other. In fact, not almost creates it, it does create the other based on these statements, these 4 physics facts. One of them will create another. Again, here is that same kind of pathway, these same 4 bullet points. The examples are because we've seen each of these before, and here are the diagrams showing that electric field hockey, that Phet simulator where I could move the magnet around, that simulator where if I had electricity moving through it created a magnetic field, and then the last one I showed you where if I moved that bar magnet it would cause electrons to move. All of these steps will create eventually one another, which is very interesting and not super intuitive, but that's the end of this part 1. All right, these 4 physics facts, all right, magnets will create eventually electricity and vice versa. If I have electricity, that can create ultimately a magnetic field and potentially even move some magnets. This has huge implications in physics and in real life. My last slide, admittedly, is not very important, okay? If you go on to a career in physics, if you study physics further, you might learn something known as Maxwell's equations. We are not going to get into this in our physics course because these equations require calculus to understand, and it's some challenging calculus at that. But these 4 physics facts are actually kind of the in-words version of 4 calculus-based physics equations that are describing this phenomena. So again, we're not actually getting into this in this class, but just know this is a big physics topic, not just in like high school physics. This is a major and very fundamental idea. All right, but these are the core notes. In the next video, we're going to see some nuances. Thanks a lot for watching this video.